Okie dokie. That's weird. Whatever. Did Will drop off? Is he still in here? Yeah, one of my 11 a.m. students just joined the the class. I think he dropped off. Maybe he's in another Zoom class at 8 and clicked the wrong link. All right. Am I recording? Yes. All right. So let's keep going where we were going. So last time we again, still building in foundational information. So I know some of you maybe already know some of this stuff. Hopefully I'm interjecting some things that you didn't already know, but for the rest of you, we're hoping that we're building that computer science foundation that you maybe didn't get from an undergrad. But I'm going into pretty decent detail on some of these things, so I'm pretty confident that all of you are getting something out of it. So in any case, actually, hold on a second. I'm gonna put my posture thing on, otherwise my back will be killing me at the end. It's like having to put my uniform on like I'm a jet pilot and strap everything in. All right, so last time we talked about network address translation, kind of the idea where you have non-routable and routable IP addresses, where a majority of the IP addresses that we're going to be exposed to with our computers are likely going to be non-routable, which means they're only unique in our local area network. And we're going to be reliant on some other piece of equipment, usually some form of a router, that's going to be making our requests on our behalf to the internet and then routing it back to us. And that thing's called network address translation, or a NAT. So something that is often not known about, but something that is extremely common. All of you are probably using it every single day, would be my guess. A majority of you, your internet at home is probably wireless. You probably have a $30 Netgear or Linksys wireless router somewhere in your apartment. That thing's running a NAT. That's what it does. It does this. So inside your apartment, you have non-routable IP addresses, and it's making all your requests for you and then sending them back to the correct machine. All right. We talked about BitTorrent, kind of the idea of that, how that's working. Again, I think when we first talked about BitTorrent, somebody had mentioned that it's a peer-to-peer network. So we kind of have two different classifications of networks. We have peer-to-peer networks, and we have client-server networks. Historically, client-server networks, in fact, I'm going to actually throw that into the two types of network, I'm going to call it architectures. And you probably could get 3 or 4 other types in here with like hybrid-y type things, but I think these are the big pictures. We have peer-to-peer and we have client server. Historically, client server was how all of our networks worked, where you had one server computer with all the client computers connecting to that single server. And realistically, inside of a local area network, that's probably acceptable. But now that we're starting to use the internet, well, I say starting, we've been using it for years and years and years and years now, but we're dealing with a more limited bandwidth. And our expectations of that network are higher. So a single server, especially given its internet connection, might not be able to adequately serve a high number of clients, because those clients are going to have their download throttled down because of the server's inadequate upload speed. So we're going to call this old school, where peer-to-peer is more of our new school approach, where we spread the wealth over the internet where if we are involved in a network experience that has multiple users using it at once, maybe we offload some of the heavy lifting to other clients on the network rather than the server. And maybe the initial server is the one who kind of makes those peer-to-peer connections. So we're not dealing with it in terms of data transfer as much as we're dealing with it in terms of just computational handshaking or something like that, where it kind of is, just gets the job done. It connects you up to all the different things, but not really moving tons of data. Because servers are still very, very, very good at doing a whole bunch of tasks at once, right? If you think about, a foot race, who wins the foot race? Your Intel Core i9 or Core i7 processor, or your internet connection? Your Intel processor wins that foot race. So our computer processors are really, 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 really fast. And many of them, I think I've shown you in here before. So this is my setup on a laptop. So I have an 8-core i9 with 16 logical cores. So I can do 16 simultaneous things, each one running at 2.4 gigahertz with turbocharge, yada, yada, yada. But in any case, this computer has a really, really, really fast processor in it, probably among the fastest consumer processors that's out there. You're not going to find an internet connection that will keep up with the computational abilities of this laptop. So we can still rely on our servers to do a whole bunch of computation stuff and keep up with a lot of clients simultaneously. Let's see, sorry about that. And keep up with a lot of clients simultaneously. So we're going to say still used for computational solutions, but phasing out for, we're just going to call it internet bandwidth solutions. So whenever we're talking about internet bandwidth, we're probably trying to share the wealth across many peers. Now, even having said that, let me just ask a follow-up question. Are there computational solutions that can't keep up with demand for the number of simultaneous users? So on the internet today, are there things that happen on the internet today that a single server could not keep up with the number of simultaneous clients from a computation perspective? We're not talking about moving a whole bunch of data. We're talking about being able to handle an adequate number of incoming connections. So can you give me an example of something on the internet today where a single computer server might not be powerful enough to handle the demand of the number of users who want to use it at the same time? Anybody have an example of that?
Downloading of a file, multiple users downloading it at the same time.
Okay, so the downloading, I want to move away from the bandwidth side. I'm talking about the computation stuff where, let's say you have 10 million users all trying to connect to a single computer at the same time. Is there any example on the internet today where you might have that number of users who are all trying to use resources from a single computer at once?
It's a client server kind of topology where in the modern days we have a cloud data warehouse where enterprise systems users log in from multiple locations.
Okay, and so that's the solution to this problem. So what kind of place, give me an example of a company that might need to rely on that cloud server thing, which we'll talk about. But can you give me an example of a company that probably uses something more than just a single server to provide their services?
We have YouTube, LinkedIn, Twitter. All these are big.
Microsoft,
Okay.
AWS.
Okay. Yeah, so those are the server providers like Azure from Microsoft, AWS from Amazon. But so for instance, all of you in here, I'm guessing at some point in the day you use Google, right? There's a couple of you that might be Bing users or something like that, but probably a majority of us use Google as the search engine, right?
Yes.
So how many people do you think are doing Google searches at the same time as you're doing a Google search?
Millions, if not billions.
Yeah, a lot, right?
Yeah,
we'll round down and say a lot. All right, so we got a bunch of people all trying to do the same thing. We're asking the same question to, presumably, by the old architecture, a single server. And even though we're not using up tons of network bandwidth, right? Because I mean, the amount of data that's being sent when you're just requesting, you know, the score of the latest cricket match isn't a whole lot. Now we're back to that example where we talked about like how much data needs to be moved across the network for like Call of Duty, like a video game. We're not really moving tons of data, but we're reliant on that network's ability to move small amounts of data quickly. In this example, we're talking about a computer's ability to handle many incoming connections at once. Those individual connections may not be all that demanding in terms of amount of data. Obviously, it does add up, you know, kind of have death by 1,000 cuts, where, you know, if you have, you know, 100 simultaneous connections all asking for 1 kilobyte of data, well, now you're at 100 kilobytes of data. That starts adding up pretty quickly, and then you could start maxing out your internet connection. But the fact that you're trying to service 100 or 1,000 or 1 million simultaneous connections using a single computer, that single computer can get overwhelmed, even though our modern day computers are really, 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 really fast, right? And when we can't make them any faster because of heat, what do? We just add more cores. So now we have, well, it's no faster, but we give them some brothers. So, you know, he's got helpers to deal with the same stuff at the same time. All right, so we might say here an example like, you know, Google has too many simultaneous requests for a single server. We're going to say doesn't matter how powerful to handle at once. So what is the solution? All right, and you mentioned some of these things. So kind of early solutions were server farms, where incoming connections were routed to one of a bunch of servers that were leased busy at the moment. All right, still dealing with a single you know, a single location. But, you know, maybe Google said, okay, instead of having a single server, we'll have a warehouse with 100 servers in it. And when all those incoming connections come in, we'll just hand them off to one of those 100 servers that's least busy right now. So we're kind of load balancing those requests across a whole bunch of individual computers. All right, so maybe that makes some sense. All right, then we're going to say upgraded solution moved the server farms to regional locations where requests were forwarded to the most, we're just going to say efficient in quotes, geographic location. And that could have happened on the front end or the back end. So if you're in France and you do a Google search, you're going to hit Google's regional servers in the closest to France, as opposed to coming all the way to, you know, their servers in the United States and then getting thrown back to France. So they're and we're going to talk about how that happens through something called DNS here in a few minutes. But you know, the idea is that we'll put server farms at lots of different places on the planet and try to make sure that you're going to get connected to the regional server farm that is the most efficient speed connection for you. Reasonably speaking, if you have a server farm that's 20 miles away from you, that's going to be a whole lot better than having a server farm that's 10,000 miles away from you. Even though we can't necessarily think that 20 miles away is necessarily that much shorter than 10,000 miles away. It probably would be in that case, but our internet kind of works like the airport, where sometimes you're flying from point A to point B and they fly you through another airport, which doesn't seem very efficient. Milwaukee being a good example. So a lot of times if you want to fly to some places in the country from Milwaukee, let's say I want to go to some like Los Angeles, which is on the West Coast. And I'm flying out of Milwaukee. Well, there are some direct flights to Los Angeles, but it would be possible that you'll fly from Milwaukee to Atlanta first on the East Coast, and then fly from Atlanta to Los Angeles on the West Coast. Now that doesn't seem very efficient in terms of, you know, you're adding a whole lot of distance to that trip, but that's the way that your trip was routed. Because of, you know, the particular flight you were taking, that kind of stuff. Okay, and we'll talk more about that when we get into the DNS stuff. All right, so upgraded solutions, move the server farms to regional locations where requests were forwarded to the most efficient geographic location. And now really what we're doing is we typically call this cloud solutions today. You know, it's common when, especially I think about explaining to my parents, like, what's the cloud? You know, we think of it as being, you know, clouds are up in the sky. So the data that's on our computer is duplicated up in the cloud somewhere, where it's not on our local computer, it's stored someplace else. And my parents would believe it's stored in space or something like that, which would be possible. We're throwing satellites and stuff up. Okay, but generally speaking, what we're doing is we're using storage area networks at one of these regional locations from one of the cloud service providers. So it was already mentioned today, for instance, you know, our big clouds today, Microsoft runs their Azure cloud. So that's one of the big boys. Amazon runs their Amazon Web Services, which has several different, well, Azure has the same thing, has lots of different cloud computing type resources, both storage and compute type resources. Google also has cloud resources, kind of an interesting spin on that. Let's go types of cloud providers. You've probably seen this before. Some cloud providers are PaaS, some are IaaS. Anybody know the difference between these two, let's call it technologies?
Yes.
Okay, what can you tell me?
So infrastructure as service is basically where we are leasing the infrastructure of or the computing power of vendors, whereas the platform is basically, for the best example I can give you is basically the database of those cloud providers that acts as a platform for us to build the computing solution.
AWS or Azure.
Okay, so let's think about IaaS. A good example of this would be Amazon Web Services. Now, I'm going to try to, I'm going to say it in a different way. I think you understand what it means, but I'm going to try to explain it maybe a little clearer. So I'm going to say you are leasing hardware / OS solutions from the provider without being bound by
Any contract.
well, not even a contract, not being bound by the mechanisms, the means that you must interact.
Like
that
upgraded or downgraded anytime based on the application.
Yeah, well, so the example would be is if I'm doing something with AWS, effectively what I'm doing is I'm leasing a Linux server in the cloud. And I can do whatever I want with that Linux server.
Yes.
You know, I can install whatever software I want to install on any kind of services I want to install. I want to run a MySQL database on there. I can do that. You know, I'm effectively leasing a computer in the sky that's not at my house, with the benefit, like you just mentioned, that that computer can on demand become more or less powerful. More RAM, less RAM, more CPU power, less CPU power, so on and so forth. All right. So behind the scenes, I'm given an infrastructure, so a computing infrastructure, and Amazon has their built-in storage technologies and things like that I can take advantage of, but I don't have to. I can just use, I can do whatever I want as if that's a computer that I own, but it's put up in the cloud where it has a non-routable IP address. I'm sorry, where it has a routable IP address, a real IP address on the internet.
A static IP.
Yeah, a static IP. Some of them aren't guaranteed to be static IPs, but a static IP address, typically when we mention that, means you have a fixed IP address and it's always that same IP address. Otherwise, you could have a routable IP address that was handed out through DHCP, which we talked about last class, which is a dynamic host control protocol where some server is handing out IP addresses to computers, but those IP addresses can be routable or non-routable, depending on.
But they change once the system is restarted or something.
Potentially. Last time we talked about the lease time on DHCP. We had a slide like how do we force our router to get a new IP address? Because a lot of times DHCP, it'll have like a 1 week lease time or something. So if you restart the server, chances are you'll get the same IP address again, depending on what the lease time is. But to your point, if you're running a legitimate server in the cloud, you want a static IP address. You want to guarantee that your IP address is not changing. Otherwise, it'll be problematic with DNS, and we'll talk about DNS here in a little bit. All right.
I have a server actually. I have a AWS account and 2 servers.
Okay. Yeah, and so what do you use those servers for?
It's for basically a .NET application hosted on it. For it's a towing service in Saudi Arabia.
Okay.
So drivers use that app to get new jobs, like Uber.
Got it.
Uber for towing trucks.
Sure. All right. So you effectively said, I'm going to use Amazon Web Services so that you have more flexibility over how you're going to solve your problem, right?
Yes.
As opposed to having to solve your problem. Let me kind of show it on the other side. So what is PaaS? What's this guy stand for?
Platform as service.
So this is platform as a service. And what's, so we're just going to say Google, Azure are examples of this. So what does platform as a service, how is it different than an infrastructure as a service?
So the best example is if we want to analyze something a report. So we are using Google or Azure's platform like Power BI or Google Analytics as their platform, and with their subscription, we are subscribing to those services and using their platforms.
Okay. So this guy provides a set of pre-built services that can be leveraged to solve problems.
It's modular also.
As well as, we're going to say, I like to call it elastic computation power. But problems must be solved in the way that the platform dictates. Okay, so for example, if you're using Google Firebase, one of their Firebase technologies, used to be called
For push notifications and
well, yeah, they do push notifications there. I'm trying to think what the previous Google App Engine. So previous to Firebase, Google had something called App Engine. But in any case, the idea here is that they are providing you not just with a Linux server in the cloud, for example, that you can do whatever you want with. Instead, they're effectively providing you with an API and a place to host your applications, and you must solve your problems using their services, their network storage stuff, their artificial intelligence, machine learning stuff, all those things. Now, Amazon, being an infrastructure as a service, they offer a lot of those add-ons as well, but you're not forced to use them. With Amazon, you could choose to just basically have a Linux box in the cloud where you are renting server space, and you can do whatever you want with that server. Where a platform as a structure or as a service, you are not getting a Linux box, for example, in the cloud. You are getting an account with a way of uploading applications, and those applications have to be written in terms of the underlying programming language that you are using, as well as the services provided by that platform. So the stuff that Google provides in terms of database storage, machine learning, things like that, or the things Azure provides in terms of the same kind of things. So you can imagine that Azure is very integrated with Microsoft technologies. So if you're a .NET developer and you're okay with always doing things the Microsoft way, then Azure would make a whole lot of sense because your life would be easier. Now, whoever it was mentioned that you have a Amazon server, but you're running a .NET application on it, right?
yes.
Okay. Why did you choose to use AWS to run a .NET application rather than Azure to run a .NET application?
It was purely based on cost. The client pays for it, so he preferred it.
Okay, got it. So you made the decision for cost. I might make the argument in hindsight. So here, I want to create a slide for your specific test case. So where to host a .NET application. And for those of you who aren't familiar with .NET, it's Microsoft stuff. so .NET means it's a Microsoft application. All right. The funny thing about, and I won't get to it in here, I'll probably talk about it in one of the other courses you'll have with me, but .NET is the suite of Microsoft applications that was kind of born after Microsoft tried to steal the Java programming language, got sued by Sun Microsystems back then. Oracle bought Sun Microsystems, so it looks like Java is a product of Oracle, which it is today, but it used to be a product of Sun Microsystems. Well, Sun Microsystems sued Microsoft, didn't just roll over, won the lawsuit. Microsoft then came out with C# as their Java competitor, let's say. Good language, nothing wrong with it. All these big companies steal from each other anyways. So, I mean, I'm not I don't demonize Microsoft. They're just a big company, just like any other big rich company. but in any case, in fact, you might, if you're trying to make correlations over the years, I think Microsoft was demonized by a lot of technology folks, and we see it. And I'll actually ask another question here in a second. But Microsoft was demonized because they had the biggest target, right? 98% of the people who were using computers are running a Microsoft operating system. So Microsoft was the big bad wolf, right? They were making the most money, yada yada yada. They had the most everything to throw around and beat up the little guy and that kind of stuff. Our equivalent of that today, right now, in kind of the in the news is Facebook, right? Or Meta. Let's use Meta as an example. So if you go and you read the news over the last many months, really over the last year, Facebook is almost always in the headlines for privacy issues or stealing data, whatever stuff like that, monopolistic practices. And part of the reason for that is Facebook is the big boy, right? You don't hear, you take Facebook, they're a social media company, right? There's lots of other social media companies. Microsoft owns several social media companies. Then you got places like Twitter and things like that. Well, all of those companies are kind of doing the same crap that Facebook is doing because they were modeled after Facebook. But they're not getting sucked into the news because they're not the big fish, right? They don't have the giant target on their back. Now, Facebook, by today's standards, is kind of like IBM was when Microsoft first came out. So Facebook's the big bad wolf in the social media space, but there's tons of other more modern social media platforms that are kind of the current cool kids. But Facebook was the dude that started it all, right? So Facebook ends up being this this giant target, and that's why they're getting drugged through the mud. I'm not defending them and saying that they're perfect angels and aren't stealing data and stuff like that, but I doubt very much that they're doing anything significantly worse than all the other social media companies are doing. They're just a big target, so they get sucked into the news, and it's actually something that I'm having to deal with clients. I think I mentioned early on in the course that I do a lot of stuff with virtual reality, and I invited some of you to, if you wanted to come and check out the VR stuff, if you haven't used it before, we can certainly arrange that. But I work with a client. This is a good example. I have a client in Madison, Wisconsin, that is looking at using VR headsets to do something that they do in their business called wargaming. So this is a business analytics company. So effectively, they're a consulting company that goes into companies and helps them decide what to invest in next in terms of where are they going to make their next dollar? Not necessarily just stock market investments, but what new technologies do you invest in? What new products do you sell? That kind of stuff. And they do this wargaming thing where it's kind of it's an organized event where they usually fly out to the headquarters of this company, and they set up like a 3-day event where they create small teams from that company, and they kind of compete against each other with these very the company in the middle asks various questions, and then there's presentations, and they basically go through multiple iterations of something until effectively a result emerges. What's the next thing to spend money on? Well, they're looking at, hey, listen, think about all the money we're spending in travel, think of all the money we're spending in hotels and the inflexibility with time. You basically need to find 3 days right in a row for all these people to do this. What if we instead just shipped them VR headsets, and then we can do the entire war game exercise completely in VR with some sort of private kind of conference type space. So we've been prototyping that with them lately. Now, I had previously mentioned, I think, that Facebook is the king of VR right now. There is not a close second, which is unfortunate, and hopefully there will be soon. But love them or hate them, Facebook owns VR. And because of that, Facebook's the tool that we typically will use for that kind of thing, like the wargaming thing, would be something called it's made by Facebook Horizons workrooms, and it's really, really, really good. It's far better than any of the competitors. But the problem is, for these businesses, it's owned by Facebook. So what you have is you have businesses that might be turned off by the fact that they're being asked to discuss corporate secrets. You know, they're brainstorming the next thing their company might spend money on. They're doing it inside of a virtual space that's controlled by Facebook, who they don't trust. So even though it's the best product, they don't want to use it because it's run by Facebook. Just kind of a, an interesting dynamic that exists today. But in any case, let me swing back to what we were talking about here, where where to host a .NET application, because you mentioned that you have a .NET application, but you're hosting it in AWS, and you said it was only because of cost. All right, so a .NET application is going
it's on a EC2 Windows server, and for testing it's on a light cell Windows.
Yep. So you're effectively renting a Windows server on Amazon.
Yeah. Yes.
Sure. Yeah, and I get it. The joke I was going to make a few minutes ago is with this .NET thing is, Microsoft tried to steal Java from Sun Microsystems. They got sued. Microsoft lost. Microsoft comes out with C#, and that's when they kind of invented their .NET suite. And it was something called the .NET component architecture. Now, leading up to this, Java's claim to fame, what Java would say is, what makes us great is that we're platform independent. You can write your Java program once and it'll run on any computer that has the Java virtual machine. It'll run on Windows, it'll run on Mac, it'll run on Linux, okay, whatever. Well, Microsoft, after they came out with C# and their .NET component architecture, they said, you know what? You write your application once, it'll run on any platform that has the .NET component architecture. Okay, just like Java said, it'll run on any platform that has the Java virtual machine. The problem with that is Sun Microsystems, they wrote the Java virtual machine for Windows. They wrote the Java virtual machine for Mac. They wrote the Java virtual machine for Linux. They wrote it for phones. So they wrote the Java virtual machine for these other platforms. Microsoft only wrote the .NET component architecture for Windows. So really, when Microsoft says it'll run on any platform that supports the .NET component architecture, they're saying it'll run on any platform at all, as long as it's Windows. So as long as you choose Windows as your platform, it'll run on it. It's just kind of a funny thing, as they used to brag about it being platform independent, even though it would only run on the Windows platform, because it was the only one that they had written the .NET component architecture for. Just kind of a funny history stuff. All right, so if we're thinking about, we have a .NET application, some kind of Microsoft-based application, and we want to host it in the cloud, we might initially lean toward Microsoft Azure. You have a Microsoft application. Probably Microsoft Azure is going to be very, very, very compatible with your Microsoft application. This might make a lot of sense. And this guy is a platform as a service. Okay, you chose. Why might we choose AWS? Infrastructure as a service. Okay, you decided it was because of cost. It cost you less to effectively rent a Windows server in the cloud than it would have cost for you to pay for the services that were being provided by Microsoft Azure to support your application, even though you had to do more of the work.
Yes.
Since you're using an infrastructure as a service, since you're using AWS, which effectively is just giving you a Windows server in the cloud, you now have to do all the work.
Yes. Yeah.
You just have a computer. You have
Yes.
a Windows computer that lives in the cloud. And if you want to install some piece of storage software on there or something like that, you got to do it.
Yeah. I have to connect through RDP and install it.
Yep. You're just using a computer. Okay?
Yes.
You're using remote desktop, connecting to it. And if you want a piece of software on there, you install a piece of software. Now, with that comes flexibility. So this kind of goes back to what we were talking about on the previous slide. IaaS, lots of flexibility at the cost of, let's say, time/effort. Okay, so with IaaS solutions, you can do whatever you want, but you're going to have to implement it yourself. PaaS, we have less flexibility, but solutions are turnkey, ready to go. Right, so you don't have to do the heavy lifting. You don't have to install something special. You don't have to do any of those things. You just have to do things Microsoft's Azure way, or you have to do things the Google Firebase way, using their platform tools. All right. So that's kind of the trade-off here. On one hand, IaaS gives you lots of flexibility. You mentioned that it's lower cost. I don't know that we can fairly say it's always lower cost. It probably does depend on the type of application you're running.
Yeah, sometimes if the traffic is high, the cost goes high.
Correct. So, I don't think we can just directly say AWS is cheaper than Azure.
Yes.
But
No,
some applications
EC2,
it might be.
yeah. The light sale version has a fixed price, like $70 per month.
Yep.
The EC2 is based on load.
Sure. So we might say cost maybe, but probably flexibility to do whatever we want and not be bound. Alexa, shut up. And not be bound by the tools provided by the platform. Why might we choose Azure, which is a platform as a service? Ease of use and implementation. That's the decision. Now, we might say at the cost of
Effort.
flexible solutions to interesting problems. For example, in the early days, Netflix used AWS to host their streaming service. Now, obviously, that went away when they became direct competitors, and Netflix got big enough to install their own kind of stuff. But why would Netflix use something like an infrastructure as a service as opposed to a platform as a service? Well, it's because Netflix's special sauce is data compression. All right. So what Netflix does, I mean, they have their library of movies and things like that. But in order for them to deliver such a high quality signal for high definition, now 4K, that kind of stuff in a package that is digestible by the average internet connection, they've had to create some really cool solutions with compression and stuff like that. Well, they would not have had the flexibility to do custom solutions like that if they had used a platform as a service. With an infrastructure as a service, they can do whatever the hell they want. They can just write their own software to do whatever. They're just going to pay for the amount of data that's moving. So kind of an interesting thing. And I'm guessing several of you are Netflix subscribers. I don't know if you saw the email this morning, but I guess they're raising their fees in middle of March. So kind of an interesting thing. They say so they can bring us more shows. All right, so that's kind of our argument there with cloud stuff and different types of network architectures. So our peer-to-peer is mostly for solving the data. So we're going to say allows us to move larger amounts of data without a single point of congestion. All right, call that a relatively true statement. All right, cloud providers, where might we host a .NET application? So we can see that it's not always cut and dry. I mean, this is a legitimate decision that a computer scientist needs to decide. You know, why might I choose one over the other based on the solution that I'm putting together? All right. All right, so getting back to where we kind of finished off last class, I know we added some stuff in here. We want to at least start the conversation about, you know, when we type in www.google.com, what happens? Well, in our browser, we are typing in www.google.com. And what I'm going to do here is I'm going to actually, let's do a trace route. All right, so I'm going to do www.google.com. And what this is going to do is going to send my request over the internet and show me what a trace route does is it shows me all the hops. I mentioned earlier that that the internet kind of works like at airports, where you don't necessarily always go in the most efficient direction. Here, I want to just use the United States one. Yes, this is not giving me IP address. It's giving me the MAC address. Actually, it's giving me the IPv6 address. I'll just do a DNS lookup. And then I'll explain what DNS is. All right. So when I type in google.com, so in the browser here, when I type in google.com, it's going to take me here to Google's website. Similarly, if I just put that IP address in there, it also takes me to Google's website. All right. So ultimately, so this guy somehow turns www.google.com into a routable IP address that needs to be connected to over the internet. In this case, that IP address is that. If I'm doing this from the United States.
So they have there is a single domain google.com, but how do they route different IPs to that single domain?
Well, because the single domain, the domain itself is google.com. And then reasonably speaking, they like the www historically would be like, that is a computer that lives on that domain. Now for Google, it's probably a whole bunch of computers, right? But we just think about it as a single computer. So you can have one computer that serves a whole bunch of different purposes. So you could have an email server on the same computer that you're running a web server, on the same computer that you're running an FTP server. So when you type in www, that would go to the domain at port 80. But you can also have www, that computer at the domain, be a different IP address than like the smtp.google.com for the for email sending. That might be another physical computer. So the domain itself doesn't actually link to a specific IP address. The domain itself is kind of like a name, and then computers on that domain have IP addresses. And you could have an A record for DNS lookups, which is for google.com. You could have a default IP if somebody just types in google.com. So if I come in here and I don't put the www in front of it, I just do google.com, it'll take me to that site. Because they decided that the default service for google.com must be www, so it went ahead and routed me to the right IP address. All right, but all this is done through something called DNS. How does this conversion work? The answer is DNS. Domain name service. So we're going to just at least define this. We'll kind of leave ourselves at a stopping point. So we'll say domain name service is a distributed network of servers that maintain, at least in part, a list of mappings of domain names to IP addresses. Now, the important thing here is this idea of it being distributed. There are top level domain servers across the world. Let me just do a lookup. There used to be 7. I'm guessing there's more than that now. Top level DNS servers in the world. Probably get a map of it. No, that's not a great map. It's a little bit older. This one might be decent. All right, this probably at least gives us enough to operate off of. So there are these root servers for DNS. Now, I promise you, there's way more DNS servers on the planet than these. All right, so these are the core root DNS servers. These guys would all sync with each other. So every single one of these servers will have all of the domain name mappings on them. So if there is a domain name that exists, it would have the IP address that it should map to. Every single one of these would have all of them. Okay. Now the issue here is that this is only 12 root servers. If the entire internet used these 12 root servers to do all DNS lookups, we'd be back to the problem we talked about earlier in class of them running out of computing resources, right? So what we have is we have, we'll call these guys root servers that have all of the domain name, IP address mappings.
So who maintains this and who owns this service?
That's actually a good question. It used to be IEEE was kind of the governing body, but I have to think they're run by independent companies now that are funding it. So I guess the short answer is I'm not sure. But I bet you they're for-profit places that are putting the money in so that they can be part of that, you know, almost a lot of data that's flowing over the internet's coming through them. Let's see, who owns the DNS root servers? So ICANN, which was an IEEE offshoot, is responsible for servers. Trust of the operation. So ICANN manages domain names, but how do they manage the servers?
They take a fees.
Yeah, for managing DNS, they take a fee, but they're running these root servers, and that has to have a pretty high cost associated with it. I can't imagine a company with 388 employees is going to be swinging that.
So maybe like service domain providers like GoDaddy, name.com, they
Well,
take up fees from us, then they give them to
Yeah, that's what I'm thinking. It's for-profit companies that are actually running those top-level servers. Yeah, but it's an interesting question. Somebody's paying the bill for those things to keep the internet running. So it is an interesting question. Okay, so these are top-level domain servers across the world, root servers that have all the domains, but we have more local DNS servers that can hopefully accommodate a large percentage of requests well before those requests are escalated up the hierarchy to one of the root servers. Let's leave ourselves a slide here. How does the DNS hierarchy work? Okay, so next assignment is up on Blackboard. I think I'm caught up on all the grading. So any of you who turned in the midterms this last week, I think it should be graded. I'll double check that. I know I was grading it the other day. I don't remember if I got interrupted or not. But in any case, the next assignment's on Blackboard, due midnight on Sunday, and I will see everybody on Monday morning.
Dr. Littman, there is a link which is provided in the discussion section for the 6th unit.
Yep.
Is different than what it is mentioned there.
Well, can you tell me what the link says? I mean, I can go look.
I think in that discussion section, it says about network sharing. But when we click that link, it is opening how to create an account in Windows.
But this is only for the discussion.
Yeah, it's for
Okay.
discussion only.
I'll check it, but for right now, you can just skip it.
Okay,
But I'll check to see why the link is taking you to a weird place. It's as long as it's not the regular assignment, just the discussion. I think that's okay.
okay.
All right. Anything else?
Dr. Lehman, this is Syed.
Yep.
Syed Moinuddin. I sent you an email with the details. If you can let me know if you have any questions or concerns on that
Okay.
topic.
Yeah, I'll take a look here in a few minutes.
Sure. Thank you.
All right, everybody have a good one.
You too. Bye.